Okay, we have the statement if P then Q. Okay, this statement says that if P happens, then Q has to happen. Okay, we want to look at the meaning of the statement if not P then not Q, where we negate both P and Q. This statement is called the inverse of our original statement. We also want to look at the converse, if Q then P. And if Q then P, of course, just reverses the order of the statement. Then we want to look at the statement that both reverses the order and negates both P and Q. This is called the contrapositive. So we've reversed the order and both P and Q are negated. Okay, well, let's take a look at a Venn diagram for the statement if P then Q. What would a Venn diagram look like? Well, we've already seen what it looks like, but let's just kind of review that. Okay, so down here, here we have a circle indicating all P events and a circle indicating all Q events. Okay, so in this case, is it true that all P events are Q events? If so, this would be a representation of if P then Q. We can look at this picture where the Q is inside the P. All the Q events are inside the circle containing all P events. Does this stand for if P then Q? What if the P events are here and the Q events are here and they don't overlap at all? Can we say if P then Q? Well, clearly there's no way. It can't be if it's this, it can't be this. If it's this, it can't be this. So that one we kind of dismiss. What if we have an overlap? Can we say if P then Q? Well, what I say here is it ain't necessarily so. Because the way we've drawn this, if there are events in this part of the P circle, they aren't Q events. So you can't say if it's a P, then it's a Q. P might be here, and in that case, P would not be a Q, so we would not want to draw an if P, then Q statement like this. Well, the only one that works, also in this picture, you might have a P out here that's not a Q. If you have a P that's not if you can have a P that's not a Q, then the statement if P then Q cannot be regarded as true, so we would have to regard it as false. The only picture that's consistent with if P then Q is this one. If it's a P, then it has to be somewhere inside this circle, and there's no way to draw to mark an event that's inside the P circle and not have it inside the Q circle, since the P circle is contained in the Q circle. It's okay that there are Q's that are not P's. This doesn't say anything about what the Q's are, whether they're P's or not, but this says that all P's are Q. Every time event P happens, it has to be also a Q event. So here's the picture of if P then Q. Now I've drawn the picture here. Again, you could ignore the statement in purple. It comes a little bit later for right now, but that's the picture. The P has to be inside the Q. Then we ask ourselves, well, okay, is the inverse true? Okay, is it true that if not P, then not Q? Well, we draw the P circle inside the Q circle here, and now I shade everything that includes events that are not P's. Okay, that's everything outside the P circle. So all the not P events are out here. What do we have? Okay, well, we could have an event here. This event is not a P, and it's also not a Q. So if we want to look at the statement, if not P, then not Q, this event would not contradict this statement, because here's a not P that's also a not Q. However, we could also draw a not P inside the Q circle but outside the P circle. Okay, so it's a Q but it's not a P. Well, in this case, it's not a P, but it isn't a not Q because it is a Q. It's inside the Q circle. So the statement not P, if not P then not Q cannot be regarded as a true statement. We say that would be a false statement in the case of this picture. Okay, what about if Q then P? Well, we come back to the purple comment now. The purple X represents a Q that isn't a P. So we can't say that if it's a Q, it's a P. So if Q, then P would be a false statement in this case. Okay, so we can say that this statement and this statement both include cases that are not included in this statement. It's possible that this statement then is not that this statement is true when this statement is false, or that this statement is true when this statement is false. So that these two statements are not equivalent to this statement. Now let's consider the contrapositive, if not Q, then not P. Okay, so here we have again, if P then Q. We want to see if it's also true that if not Q, then not P. Well, I've shaded the region corresponding to not Q. All the not Q's have to be in this shaded region, so that any not Q event that I might choose has to be somewhere in this shaded region. So here's one, and we could choose not Q's anywhere in the shaded region. It's very clear that this is also not a P, because the P's, the P events are inside the Q circle. So if it's not a Q, it can't be a P. So not Q, if not Q, then not P turns out to be true. So we can say that the statement and its contrapositive are in that sense equivalent. One is true whenever the other is true. So these are equivalent. Now, just because this is not equivalent to this and this is not equivalent to this doesn't mean that this is equivalent to this. But as it turns out, these two are also equivalent. But none of the argument that we've shown here proves that. Okay, well, the diagrams should help give you more of an understanding of these statements and their relationship. We can also analyze the relationships among these statements by analyzing their truth tables. It's very easy to analyze the truth statement of each the truth table of each of these statements, and that's what we're going to do in the next video.